Well, good morning, good afternoon, and good evening, everybody. My name is Dan Conway, and I'm going to be speaking with some of my friends about blockchain security. This is a difficult topic. Security in general is a difficult topic, and then throw in another 7 layers of DeFi stack created by people around the world with competing interests, and you probably have an even more difficult topic. So I've invited some of my friends here who are pretty high achievers in this space to talk through some of these issues with us. So if, oh wait, I've got to announce the winner from last term. So I've got 2 computers, a phone, and 6 out there, but I wrote it down on paper. Ryan Decker, congratulations. You are the winner of the last round. I believe we have one more round after we're done here, and we will, your last chance for winning these prizes. So, again, I think this is an important topic. I actually started a conversation this week with some people about blockchain and the metaverse and how security is going to look like in blockchain and the metaverse. Well, maybe next year we'll talk about that. But some of these topics overlap with the things we've already talked about. We know there's issues in trust and what trust looks like. Is it binary? Is it layered? Is blockchain a solution? Does it contribute? We have security issues with blockchain and security issues that blockchain can help with. So I would like to bring in the folks that are going to help us understand that today. And somebody out there can say, they're here. So they're here, apparently. All right, so I've asked 3 of my friends to join. Dan Geer doesn't have a camera due to good reasons. David Rosenthal and John Ryan are all going to speak. What I'll do is I'll go through and introduce quickly each of them, and then I will have, I'll start with Dan, and have Dan talk about, I'll introduce in more detail each of them when I get to their point. Then I'd really like to prioritize student questions. I think all of these people have an active role in educational systems and have been very active at universities. So I would like to prioritize student questions. But let me start with a quick introduction. Dan Geer, I've known for quite a while. I had a conversation with him about blockchain and Bitcoin when it was under $1. And we've had some interest in security that have overlapped over the years, so he will be the first one to speak. David Rosenthal is probably one of the, if you made a list of the top 5 influential people in Silicon Valley over the last several decades, David would be on probably each of those lists. I get several emails from him a week, which I prioritize and look at as obviously important. We're all kind of concerned right now with software supply chain and securing that. So David will speak second. John Ryan, who I also speak with many times a week. You may recognize him as founding principles of the decentralized web. Dave and John are in California, and Dan spent a good chunk of his life between MIT, Cambridge area, and Washington, D.C. So I'm going to have Dan come in first. I have over here on this computer things to remind me. I wanted to thank Mary Lassity, who's our director. Arkansas was at one time known as a flyover state, and then as we got digitized, it became a route over state. But because of what Mary's been able to put together here, I think we have as good of an academic center in this topic as anywhere in America. And I think they're changing the routing tables of the BGP protocols to make sure everything comes to us. And I want to thank Catherine for putting all this together. She's probably in the bathroom crying about her decision to let me speak at the moment, but when she comes out, I'll let her know that I'm grateful for that. To our guests who have never seen me dressed up before, and as an introduction to myself, I'm Associate Director of the Blockchain Center of Excellence. I was among the first 15 or 20 Bitcoin miners a long time ago. and been fairly active in this space. And I do absolutely silly things now, like buy Shibu, a new cryptocurrency, which doesn't make any sense whatsoever. So I've become somewhat irrational in some of my dimensions of the space. But the topic that brought us all together was how to use decentralized ledgers to secure the open source software supply chain. So first I'll have Dan Geer speak. Dan, I hope you can hear us. I wanted you to, if you could, kind of frame the topic of how blockchain fits in security. You yourself, your background, many people probably know you were the first politically correct person to be fired from a job. And the term monoculture, if it's ever used, is referring to that event. And people wrote columns, "Where is Dan Geer?" CISO fellow at In-Q-Tel, and keynote speaker at a lot of the major security conferences in the US over the last 20 years. Most people consider you the thought leader in information security and network security. Could you start off, Dan, by framing what you think are the important issues in blockchain and security, and what you see as how this is going to play out as best you can?
Okay, Dan, just wave at me if you can hear me well. Okay, we're good. And for the audience, I have difficulty hearing, so it may well be that when questions get asked, I'll have to ask things to be repeated or something. I've been in security for a long time, and of course, anytime somebody stands up and says, "Oh, I've been in security for N number of years or N number of decades," your first question back should be, "Well, why haven't you fixed it yet?" And that's a fair question. The amount of work that has been put into this, with sad to say, inconsistent, incomplete results, is worth noting. I don't mean to dwell on that, and neither should you, but I guess it's testimony to it being a hard problem. Of course, being a professor sort for just a second, the question is, what is my definition of security? And this is the one I've come to over time. And a state of security, you're in a state that is secure, I define as the absence of unmitigatable surprise. In other words, not no surprises, but no surprises that you can't mitigate. And this leads in a variety of directions, one of which is, well, that means that the high-end goal of security engineering in all circumstances is no silent failure. Not no failure, but no silent failure. Because obviously you can't mitigate something that you don't know is going on. And that is something that we often neglect. And in fact, there's a lot of silent failure. Just reading the newspaper, so to speak, will tell you that every time a data breach occurs, it's a whopping surprise that nobody knew that could happen, blah, blah, blah. Well, that's my point, is that the absence of surprise is not what I think we're aiming for. I think it's the absence of surprise that you can't mitigate. And of course, that begs the question of what is mitigation? In some cases, take the data breach laws. It says that if you spill everybody's credit card numbers on the internet, you're obligated to do a number of things, like notify them, like buy them, in some states, like buy them credit watch, and so forth. And if you think that those are sufficient mitigations, a combination of notification, holding harmless, and paid surveillance of a friendly sort, if you think that's mitigation, then in fact you were in a state of security, not because there were no surprises, but because there were no surprises that couldn't be mitigated. This leads in a certain prudential, shall we say, direction. My father was an accountant, a CPA, and there is a so-called Prudent Man Rule, which roughly says that don't book future revenues, but plan for future losses. And the same thing is true here. we shouldn't necessarily assume that everything works well. We should rather assume that things will break from time to time. And what are we going to do about that? Let me give an example that might be relevant and might not be. It may be something that some of you are familiar with. What was originally known as Brewer's theorem and became known as the CAP theorem, the CAP spelled C-A-P, that was later proven correct. The theorem, in other words, was proven correct. The three letters in that, C, A, and P, stand for consistency, availability, and partitioning. Consistency defined as any read of the data gives the latest write that has taken place. In other words, if you read from a database, or of course we're talking about blockchain here, if you read from a blockchain, you should get the most recent write. Availability is sort of what it sounds like. It's what everybody knows, and at any point in time, I guess I should say, irrespective of whether the read is the latest write, the client always gets a response without error. In other words, it's not as if you'll ask a question and you don't get an answer. You will get an answer. And then finally, partitioning. The P is for partitioning, and it talks about how the fact that large network systems, of course, have occasional network failures. That is to say, a failure which needs some planning to get around, because it's not as if we can guarantee that networks never partition. So if there is a partition, what you want is there to be no possibility for the whole network to go down, but this partition should be something that you are resistant to the extent of the problem statement you're trying to solve. And the theorem, the important part of the theorem, the reason I was building up to all that was that Brewer's theorem, or the CAP theorem if you prefer, it says that a distributed system cannot simultaneously provide consistency, availability, and tolerance to network partition. That's one of those classic examples of, everybody's heard this: fast, cheap, reliable, choose two. It's one of those kinds of examples where you cannot get all three. Now, you can get close to that, and that's, of course, the design question, and that's sort of what we're here to talk about, is design questions. Blockchains would seem to violate the CAP theorem in as far as it would seem on the face of it that they must have consistency. That is, you get the latest write. It must have availability. We're talking money here. And it must be resistant to partition, because after all, this is a decentralized system that spreads everywhere and networks go down, as we all know. So is it true that the blockchain, as currently thought of, inherently violates the CAP theorem? And the answer is no. No, with caveats. And that's what I was going to mention. A blockchain, so if it is a kind of choose 2 out of 3 situation, we're going to have to tolerate network partition, because that's an external influence. So ordinarily you think of this as either choosing consistency and partition tolerance at the cost of availability, or choosing availability and partition tolerance at the cost of consistency. And how would you choose that? Oddly enough, this is a choice on the client side. And the trick is what many of you will have heard or read, and that is eventual consistency. That the idea is that the blockchain may not be consistent at any given moment, at any given second, at any given read, but it will eventually be consistent. Not instantaneous, but eventual. Or you can go for instantaneous consistency and partition tolerance, but at the cost of availability. So you ask a question, and we're going to assume for the moment that you've got to be partition tolerant. And the question, and therefore the design point, and it's a security point in my view, the design point is, do you want consistency or do you want availability? And are you willing to trade off the one for the other? And the answer is you have to. Back to the theorem. If the theorem is true and it has been proven, then you have to. In an AP client, availability and partition tolerance, eventual consistency means that as a developer, you get to choose how many blocks into the chain the block you care about is. Is it 3 blocks in? Is it 6 blocks in? There's a nice paper from Microsoft that argues that 6 blocks is a reasonable number, but I want to remind you, that's a probabilistic decision on your part. There is no guarantee because, again, the CAP theorem is what it is. So you have to decide what, in effect, the probability of failure you will tolerate is. And that goes straight back to my definition of security, which is the absence of unmitigatable surprise. If you can mitigate a failure 3 blocks in, then that would be your design point. If you can mitigate 1 6 blocks in, if you can mitigate 1 block in, but that is an example of planning for less than perfect operation as part of having the ability to mitigate, if you want to call it that, a failure. If you go and read the top block, the end block, the end of the chain, and shortly thereafter it changes, was that a failure or not? No, it's not a failure. It's inherent in the protocol. But on the other hand, if you took action based on a read of the last block in a chain, and that block in the last block in the chain changed, then you have a mitigation problem. I'm going to let that go, but you get what I hope you get what I'm driving at, which is sometimes in security, there is not available an absolute. There is not available something that says, if you do this, then that. This is a probabilistic example, and I think it applies to today's discussion. Let me do a second topic just for what it's worth, and I'll let it go at 2. And that is, who do you trust? Mr. Conway, I believe, used the word trust a moment ago. I would like to think that I trust people against whom I have effective recourse. This is the trust but verify thing that was so famous when the president said it. It's also a situation that we will face in lots of ways in the AI world, which is not today's topic. But if you have effective recourse, that's one thing. And if you don't, you have to plan for that otherwise. So let me ask you this. What mitigation, back to my favorite word apparently, if any, can be enforced if a stolen bit of data, if data loss is immortalized in immutable storage, such as blockchains? If I steal a picture or a piece of information or something that should not be public, and I somehow or other managed, and I'm sure you know that this has happened, it has happened, somehow I managed to stick it in a blockchain, I can't get it out again. The immutability, which is both a feature and in some circumstances a bug, would imply that stolen data immortalized in a blockchain can't be recovered. Of course, to a degree, data is never unrevealed. Once it has been revealed the first time, it's never unrevealed, and I admit that. But I think blockchains in their immutability are a special case, or except perhaps an extreme case, that there is, excuse me, I was babysitting grandchildren, and there's nothing like grandchildren for being germ magnets. So do those who manage blockchains which don't have a delete mechanism, do they have some sort of strict liability for the consequences of the blockchain being used to publish illicit, inaccurate, or harmful goods? And if they don't, is anybody liable? And if so, for how long and how? This is a question for democratic societies. I don't think it's a question for autocratic societies. I think it's a question for democratic societies. And in fact, an awful lot of progress being made these days, whether we're talking about blockchains or we're talking about AI or we're talking about synthetic bio, there's a lot of things where the choices a democratic society would make are different than ones that an autocratic society would make. So I'm talking here about a democratic society. What would a democratic society properly say about data that has been immortalized in a blockchain and can't be removed? What is the proper response to that? What is, if you will, the mitigation for that? Because it shouldn't be a surprise that it can happen. It has, but let us hope that it will be a surprise if it happens a lot of times. Let's hope it doesn't. But I think we need to decide what we're going to do for that. And I think we need to decide for it in the context of a liberal democracy, not in the context of the Chinese Communist Party, if you will. Mr. Conway, I'll stop there and give the microphone back to you.
Thank you very much, Dan. Yeah, we know that blockchains have been used for command and control. We have concerns about data that we don't want distributed, such as our DNA. And it may be the reasons we don't want others to have it haven't emerged yet. Maybe they will come in 5 years as we figure out how to target things like that. So immutability is a difficult topic, and in particular, immutability when it comes to source code, because having written code since about 1972, I'm afraid, I've never done it very well. I've never written code that didn't have to go through some kind of a change and that I wouldn't want to pull back and modify. And the idea of expiring information seems to go against the blockchain architecture and so on. So these are all important topics, and I think, as you said, we need to discuss them. I think they themselves make for a full day and a full week of conversation. I'm going to go on to David, though. I wrote down a lot of questions, and hopefully the students will have some as well. David, let me introduce you with your bio, because you, like Dan, I could go through a 45-minute talk about your accomplishments, but I'm going to read it here. David Rosenthal is retired, since working with computers since 1965. He was a member of the Andrew Project at Carnegie Mellon that pioneered campus networking, early employee at Sun, and I believe CTO later. Major contributor to and part of the initial release team for the X Windows system. That must be how you and Jim Geddes know each other. Employee number 4 at NVIDIA. Nearly 2 decades worked for Stanford Library and Digital Preservation. But at the prestigious 2003 SOSP workshop, he and his co-authors received the Best Paper Award for Decentralized Consensus Mechanism using Proof of Work underlying the LOX Digital Preservation Network. Lots of copies keep stuff safe. One of my favorite acronyms. This is more than 5 years between Satoshi Nakamoto published a different consensus mechanism using proof of work underlying blockchain, many other consensus protocols. I told Dan I don't think he was Satoshi back when Bitcoin was under $1, because I did some text analysis work, and Dan's writing is distinctly more punctuated than Satoshi. I don't think you're Satoshi either, because you wouldn't have created such an environmental hazard as Bitcoin, but you certainly could have. You had the technology. But David, I'll let you take the floor. Feel free to comment on anything that Dan said. I know you and we wanted to talk about the broad term of blockchain permission versus permissionless. So I'll let you take the floor on this.
Thanks. Because I'm old, I have to prepare my presentation, so it's up on blog.dshr.org with the links to the sources. Yep. Blockchain is unfortunately a term used to describe 2 completely different technologies, which have in common only that they both use a data structure called a Merkle tree, commonly in the form patented by Stuart Haber and Scott Svernetta in 1991. It's a linear chain of blocks, each including the hash of the previous block. Even more unfortunately, the more secure way to implement trustworthy public databases using Merkle trees isn't called a blockchain, so it doesn't benefit from the tsunami of hype that surrounds the term. Permissioned blockchains have a central authority controlling which network nodes can add blocks to the chain, whereas permissionless blockchains such as Bitcoins, do not. And this difference is fundamental. Permissioned blockchains can use well-established and relatively efficient techniques such as Byzantine fault tolerance to ensure that each node in the network has performed the same computation on the same data to arrive at the same state for the next block in the chain. This is a consensus mechanism. In principle, each node in a permissionless blockchain's network can perform a different computation on different data to arrive at a different state for the next block in the chain. Which of these blocks ends up in the chain is determined by a randomized, biased election mechanism. For example, in proof-of-work blockchains, such as Bitcoins, a node wins election by being the first to solve a puzzle. The length of time it takes to solve the puzzle is random, but the probability of being first is biased. It's proportional to the compute power the node uses. This fundamental difference means that the problems of securing the two blockchains are quite different. A permissioned blockchain is a way to implement a distributed database. Securing it is a conventional problem. You need to ensure the central authority doesn't admit bad actors. You need to ensure that each node is under separate administration with no shared credentials to guard against compromise. Ideally, each node should run different software to guard against supply chain attacks and so on. But securing a permissionless blockchain is an unconventional problem. Because anyone, even bad guys, can take part, its security depends primarily on ensuring that the cost of a successful attack greatly exceeds the rewards to be obtained from it. To succeed, the attacker of a permissionless blockchain needs a high probability of being elected, which means that they typically need to control a majority of the electorate. Making this control more expensive than the potential reward for an attack requires that being a voter be expensive. This has a number of consequences. First, there's no central authority to collect funds to pay the voters, so they need to be reimbursed by the system itself via either inflation of a cryptocurrency or transaction fees, or both. Currently, Bitcoin miners' income is around 90% rewards, i.e. inflation. Research shows that a fee-only system, as Bitcoin is intended to eventually become, is insecure. Imposing costs with proof of work, as most cryptocurrencies do, leads to catastrophic carbon footprints. Alternatives to proof of work are vastly more complex and extremely difficult to get right. Ethereum has been trying to implement proof of stake for 7 years. And thirdly, information technologies have strong economies of scale. The more resource a voter has, the better its margins. Thus, successful permissionless blockchains are centralized. 3 to 4 mining pools have controlled the majority of Bitcoin mining power for at least 7 years. The advantage of permissionless over permissioned blockchains is claimed to be decentralization. But in practice, this is an illusion. The enormous costs of attempting to avoid centralization are wasted. A Byzantine quorum system of size 20 could achieve better decentralization than proof-of-work mining at a much lower resource cost. Ethereum has been even more centralized than Bitcoin, and because it's a programming environment, its attack surface is exponentially greater. In particular, as we see in the recent $600 million attack on Poly Network, it's much more vulnerable to supply chain attacks of the kind that Munin defends against in other environments. Actually, centralization is often a good thing. Mistakes are inevitable, as Dan was saying, as we see with the recent $900 million oopsie at Compound and the subsequent $67 million oopsie at Compound, or the way Bitfinex paid $23 million for a $100,000 transaction. Centralization of Ethereum allowed Poly networks to convince miners to make most transfers of the $600 million loot very difficult and persuade the thief to return most of it. Immutability sounds like a great idea until you're the victim of a theft. The less vulnerable way to implement a trustworthy decentralized database is shown by the certificate transparency system described in RFC 6962. It's a trust but verify system, which is typically a much more appropriate model for business than immutability. It allows for real-time verification that the certificates that secure HTTPS were issued by the appropriate certificate authority and are current. In essence, it's a network with three types of node: logs, which record the Merkle trees; monitors, which check that that new entries have actually been added to the Merkle tree; and auditors, which check both of them. And as with permissioned blockchains, a few tens of nodes provides adequate decentralization. A key point is that clients verify certificates against a random subset of the tens of nodes that they trust, which for each node is a different subset of the whole set of nodes. Thus, an attacker has to compromise the vast majority of the nodes to avoid detection. This aids efficiency by optimizing for the common case when no attack is taking place, while still providing a very high probability of unambiguous detection while an attack is underway. Note that unlike a blockchain, this is not a consensus or an election mechanism. It's a mechanism for ensuring that none of the actors in the network can escape responsibility for their actions, which in many cases is what's needed. For example, there's a paper by Hoff and Carl showing how the same mechanism can be applied to securing the software supply chain, which is my handoff to John.
All right. Well, thanks, David. I would love to have an entire conversation or an entire workshop on the environmental impact. I've had a few questions come in from students about that, and I can point them in to your writings on the topic. I have to believe that your writings are extremely accurate. I was trying to finish a paper last week and looking up the price of storage over the years and came across your documents from 20 years ago that are still widely cited in that topic. Yeah, regarding centralization, I am active in the secret network, and we all love decentralization until something goes bad, and then we want them to roll it back so that we can get our resources back. Same things with regulation. Yeah, we don't want any until we do. So that's happened to me a lot in my life. Well, thank you. We'll get back. I've got a set of questions that have come in, and I want to get to John and have him talk briefly. John, I'm going to read your bio as well. I can talk with you every day. I've known you for a while. You don't even write down that you're a Google executive on this thing, but John has founded and run several tech companies. He spent 14 years of his career building and running a telecom consulting and analysis firm. He, with his wife, pioneered fabless display development at Pixel Q Corp. He co-created a set of principles for the Decentralized Web Project. I'd encourage all students to look at the Decentralized Web Project. I think you can do a search for John Patrick Ryan as well. Co-founded a San Francisco-based fintech project, Banyan Infrastructure. Today he leads Munin, a startup with innovative idea, creating secure software supply chains. One of the conversations earlier today, John talked about trust, and Dan talked about it a little bit, and trust doesn't have to be a binary thing. We think of one blockchain and how they've implemented a trust model within one blockchain, but that's kind of a simplistic and a limiting way to think about it. I'm going to let you take the floor and speak your ideas on this. You work every day along the lines of securing software using DLT, and you have a lot of great ideas that if you would share with our students and others. Thanks.
Thanks, Dan. Thanks, David, and thanks, Dan. Actually, for those who, it really is astonishing writing that David has put together over the last decade plus. So blog.dshr, I think that's your full set of initials, David, .org. Yeah, terrific reading. And thanks. I want to go back to remind us of what Dan Geer said at the outset. Security is the absence of unmitigatable surprise. And in this context now, thinking about what we're trying to do inside the Munin project. Munin is the Gaelic word. Dan and I have Gaelic backgrounds for trust. It comes from actually a Gaelic expression. And Cuir Munin Clave Brushta, place no trust in a broken sword. Part of our goal is to enable mitigation. And to do that, you have to be really good at looking at all of the metadata surrounding code. So this is a software supply chain analysis project that we have. One of the people we spoke to in the Department of Defense observed that Safeway knows more about the broccoli on its shelves than some companies do about the missiles, the software in the missiles that they're manufacturing. And that lack of knowledge means that there's no ability to secure or mitigate. And in contrast, one can create a good understanding of what code is and how vulnerable it's becoming by getting very, very good with the metadata of code itself. And that immediately then asks the questions of what is proportionate? How flexible do you have to be? How do you enable mitigation? So I love the reference to the CAP theorem, because in some senses, enabling mitigation enforces flexibility, but that then means you have to make it somewhat easier to let the drawbridge down on the castle, so to speak. And our goal, in fact, has been to, as David implied, and the way we do fundamentally believe, that one has to one has to make the job of attacking code more difficult. And so our approach uses decentralized ledgers in multiple ways, one of which is our own analytic engine cannot exist as a centralized object, but has to have multiple instances. The statement of what code exists in a block in a package also needs to exist via several paths. And then similarly, the reports as they're delivered to users must similarly exist in multiple copies, so that as David said, it's not that you're making it impossible, you're just making it really difficult, and eventually the risk-reward project for the attacker starts to feel wrong. And so our approach has been very much one of building a thorough picture of the metadata and doing analysis of it using a sequence of ledgers protected from each other and protected from attack. I'm going to now just sort of put some numbers to the scale on this and why we think this is appropriate. A typical large package used in building the web front ends for a bank or another enterprise might be Axios. Axios looks like a thing when many enterprises download it and start implementing it. It actually has about 500 components developed over the course of about 8 years. That's interesting in the sense that what it does tell you is that it's complicated. Many of the users do not actually have the competence in their own organizations to thoroughly scrub it, to really analyze it and say, whether this part is vulnerable or that part is even appropriate, or this other part can be completely disregarded because we're never going to use that function. Or to see if there's an appropriate level of maintenance going on. One thing that we have found to be quantifiably true is that the axiom that exists in open source, often described as the many eyes theorem, that by having things open, many people, including the original authors, will keep an eye on it. You can quantify that that's not true. People who create things like to create them, and then they go off and create something else. And as a result, one can quantify the deterioration of the maintenance of code. What you can't do easily is correct for that. So part of our goal has been to enable mitigation, not with complicated hard locks on the door, so to speak, but by putting flags in front of the end users that say, no, you really shouldn't use this. This piece of code is starting to rot on the vine. Enabling visualization and interpretation of the state of code is what enables mitigation. And that's a fundamental part, is to remember that in the end, the fundamental decisions on the utility and security of code, those decisions have to be in front of people. So raising a red flag and saying to people in the CISO organization, this piece of code is now starting to rot. This piece of code no longer feels appropriate. Doing that early, before the vulnerabilities, before the exploits show up, that's our goal. And that's what we believe one can get to. It's a project that requires careful use of decentralized ledgers, but it also stays away from immutability. It's hard to imagine, let's say the Axios project again, 500 elements, that one would actually want that any of those to be nailed down and fully immutable, since most of the users will want it to evolve over time. So that's the quick summary of our goal: flexibility and rapid mitigation of surprise. Back to you, Dan.
Well, thanks, John. It's all of us are working toward the SolarWinds attack was a devastating attack. I'm not sure if it received enough media attention, but it basically, for 3 months, all the communication at the highest levels of government were compromised. So it was as bad of an attack as we've ever had on the United States from an information point of view. And we need to fix that. We need to solve this problem. And that's one reason that we've come together, is to try to solve that problem with some of our other friends. So thanks for your work in that. And I agree that immutability has its role. We said it makes sense in land deeds. It may make sense in other spaces, but immutability maybe plays one piece of an overall layered approach to security. And again, blockchain security. And I tend to believe this new DeFi stuff is a full employment act for information security people. We already had 500,000 information security jobs available in the United States, cybersecurity jobs, and now we've got 7 new layers, not created by VentSurf, but created by people around the world with competing interests, that now we're going to have to secure a stack on top of our 7-layer model or 5-layer internet OSI model. I think there's going to be opportunities in the future, but I think the more people understand where immutability makes sense and where it doesn't make sense, I think we're better off with that. I do have a few questions that have come in. I know we only have 10 minutes overall, because I have 8 people around me telling me that. But Dan or David, Dan, I know you can't talk about a lot of the things that you see. You do the NSA paper of the year. You report to our highest officials in government and so on. But what do you see impressive going on? What do you think the initiatives going on? What do you think is really exciting? And from the point of view of students, what direction should they move in? I don't know if we have audio from Dan right now or not. I could email him a question. David, I'll throw that to you. What do you see as kind of exciting in this space as things that are initiatives? And I know you're well on track of all this. What do you think's very interesting, has got your attention?
Well, I think if blockchain really is going to be a big part of the future, it needs a better a mechanism than proof of work. And it's pretty clear to me that the current attempts to do this don't work well. It's just extraordinarily complicated. There's proof of stake, proof of stake is essentially a way of guaranteeing that the rich get richer and everybody else gets poorer. And proof of space with the Geer network has turned out to be as big an environmental and supply chain disaster as proof of work. You've got a fundamental problem, which is you have to have, if you're really going to have permissionless blockchains, things have to be expensive. You have to waste real resources, or it's not going to work. And finding a way to do that without the environmental disasters is just an incredibly difficult and important problem.
Well, it's disappointing. I was really excited with ChiaNet that the return of the Lisp language, I thought, oh good, I do have some skills that might be useful today. I was kind of hoping that that would be successful. I hadn't heard that the proof of space, they had a proof of space and time originally, I think, and they migrated to proof of space. I kind of hope that one would solve some of these problems. I have a question. David, I'll take this one to you. I think Dan's not able to hear this right now. Do you believe sharding is the solution to the pitfalls of proof of work? Solution to also security as well as storage sustainability concerned. How do you feel about sharding as a solution direction?
Like I say, you've got to make it be extremely expensive. Yeah. There's academic economics research which says that the reward for mining a block has to be bigger than the value of the transactions in the block, or there are theoretical attacks. The problem is you have to make it expensive, and that means you have to use real resources to the mining a block has to involve using up real resources, and that's a fundamental problem. If you don't do that, it isn't secure.
Thank you. Let's see. We have a few other questions. John, I'll ask you this. The University of Arkansas is developing a new cybersecurity major. What would you put into this curriculum? You are as well connected out there in San Francisco area. What would you look for in a student? What skills would you like them to know in order to be to market themselves well?
I'm sorry, was that question aimed to me, Dan?
Yep, for you. What characteristics of a student would you like to see? Would you hire?
Oh, sorry. I had to switch machines because the cable network went down, so I'm on my phone now. Okay. So apologies for that and for a different appearance. So there are a couple of ways of thinking about that. The first, of course, is the rigorous engineering abilities, the ability to code, and the abilities to think about the kinds of problems in the ways that David and Dan Geer spoke to. One other thing that I would strongly urge, though, is that people not be narrow in their thinking. That one way of thinking of this is that blockchain are the kind of security technologies that David Rosenthal and others have been pioneering for 20 years. The basics of that have in large part been created and can be refined. What happens now is going to be analogous to, let's say, I don't know, decades ago, the creation of CMOS technology. What follows from that is the building of broad, scalable, usable applications. And those require both a sort of a systems thinking and a level of user thinking, and even a humanities thinking. So I would focus not only on the hard engineering, but also on a rich user experience and application set.
Thank you, John. My PC is threatening to reboot on me too. How do they always know when not to do things?
Like my dog.
All right, I don't know if Dan can hear. I sent him a quick note, but Dan, if you can hear me, could you give a closing statement and again, encouragement to students? What do you think they should be focusing on in this area if they want to do this for a living? Dan may not be able to hear.
I got your note, and I assume you're doing that. Closing statement.
Please.
I guess I would say that how shall I put this? We can easily overrun our capacity to verify. And I don't care what we're talking about here. Software security, let's just say that, for example. We can easily overrun our capacity to do so. What does that mean? In the AI arena, explainability is a topic of great import. If you say, why did my algorithm make this decision? The answer can be true and unintelligible, or it can be intelligible and likely to not be anything other than a simplistic version of what was true. That's an example. With software, I have great hopes for the reproducible build idea. Mm-hmm. That if we make open source ever more part of what we do, which it seems to be the case, how do you know that what's in a particular use of that has not been monkeyed in some way? And the reproducible builds idea goes in that direction. In the burgeoning expanse of information of things, the amount of data, of course, is great. Everybody knows that. The question is whether the power of that data is additive. In other words, I've got 100 sources, I add one, is that 101 units of something? Or is it an exponent in some equation? In other words, it was x to the 10, now it's x to the 11. I think that merging data fusion, if you will, is more powerful than we think. And again, this is a challenge to democratic societies. It's particularly a challenge if we're not able to verify parts of how the data is acquired or used. So if you are willing to define security broadly enough to touch the things that I just mentioned, that's where I think the challenges are already and will be more so in the future. Good enough?
Thank you, Dan. Your comments are always very thoughtful. I will share on our LinkedIn or on our YouTube a link to some of your other writings, which are also extremely thoughtful. I want to thank all the panelists here. I know I'm down to about a minute here. Thank everybody for joining on this. Again, this is as good of a panel in any topic as you'll see in America. And these are people who are wonderful, work with students. They're all happy to engage with students and so on. And I'll share some of the links to their efforts. We do have one more two truths and a lie thing, I believe, that is available on one of these machines over here doing something, talking to my phone apparently. So I encourage you to get back on that. I think the plan is for us to take a minute off here and switch, and so the very brief break, enough time to do what you can do in a minute. And we'll come back after that. But thanks again, John and Dan and David. I very much appreciate your time. And I will always remember the things that you've taught me over the years, and I'm grateful for your friendship. And we'll be back.